Hello everyone, welcome back, and for today's lesson we will be looking at AC circuits, also known as alternating current circuits. So for today, let's do a bit of a background and then we'll answer a couple of questions, and then you should be good enough to attack other questions from there. So where does your electricity come from? So basically, it comes from a motor, right? So sorry. So where does your electricity come from? So energy cannot be created and destroyed. This is known as the conservation of energy. So basically, for example, if you make a fire, what you put in, such as the wood and stuff, is ignited and it burns and creates a fire. That then turns into heat and light. So when that turns into heat and light, the energy is converted, and it's not created, but it's converted from the organic material of the wood, is converted to the flame, the heat and the light. Okay, so take for example, we have our mechanical devices, right, such as a fan, right? So what that fan is doing, it is converting, so our fan is converting the electrical energy into mechanical energy, which is your cool air. So to generate electricity, what we're going to do is we're going to input electrical energy into we're going to rotate the motor, right, mechanically, and then we'll generate electricity. So what they are doing is they are increasing the scale by introducing a bigger motor and increasing the force and the mechanical energy. They are increasing it by using steam turbines and other methods such as wind turbines. So they're increasing the force, right, to give you the electricity that you use at home. So in this chapter we are going to look at alternating current circuits and formulas, and I'll explain to you how and why and everything you need to know. Sorry about earlier, I had to apparently look out at something. Coming back, so just a quick reminder, you need to remember Fleming's left hand rule, right? So Fleming's left hand rule, sorry for my bad handwriting drawing, sorry for this bad drawing of mine. I want to tell you to remember Fleming's left hand rule, very important rule, Fleming's left hand rule. Okay, so just remember that this needs to be 90 degrees, this two fingers needs to be 90 degrees, and this two fingers needs to be 90 degrees, right? So to use Fleming's left hand rule, let's see if I can draw a better hand. So we have our thumb, we have our pointer finger, 1 2 3. Okay, so this thumb, right, is pointing in the direction of our force. So remember I said we need to convert mechanical to electrical. Yes, so by doing so we need to look at Fleming's left hand rule, and it states that this is the direction of our force, your thumb. Then this index finger, I think they call it the index finger, is for your magnetic field, right? Magnetic field, right? And it points in the direction from north to south. And then this finger, the middle finger, points in the direction of the current. And remember, all fingers needs to be 90 degrees from each other, very important. And now moving to our electric motor. Okay, so looking at our electric motor, we have let me draw a simple diagram. This is what I normally draw. We have copper wires, right, running, and we have electric current going this way and electric current exiting that way. And we have permanent magnets over here, right? Permanent magnets. Let me draw it like such. Our permanent magnets inside our electric motor, and over here we have our commutator, and I'll explain that right now. So if you use the left hand rule, right, north to south, and we use our left hand rule, and these lines you can ignore them because they are producing zero force. The reason for the zero force is they are parallel to the magnetic field, right? So our magnetic field lines are going from north to south, our magnetic field lines, right? Now these lines are perpendicular. These lines are perpendicular to your magnetic field lines, and because they are perpendicular, they are going to create a force. So if you use Fleming's left hand rule, you will see that there is a force that's created, right? And I'm not sure if I can do it on here, but you can do it for yourself. Follow the magnetic field lines I showed you in the current direction of the current. Also, it's over here, and direction of the current is over here. So if you use Fleming's left hand rule, north to south, currents over there, north to south, currents over there. So this side of the circuit is going down, and once we come on the other side of the circuit, the current, the force is going up. So we have a force going up and a force going down. And because there's a force going down and a force going up, what we have is a rotation. So this rotates, and normally there would be a shaft in the middle here. A shaft, that is your electric motor. There will be a shaft here in the middle which you have to rotate, right? So explaining the commutator. So what happens is, once you sorry, wrong color, you have a north magnet and a south magnet, north and south pole, and your thing has rotated, and now it sits at this position. right? And the current now is going to be parallel to the magnetic field, so therefore it's going to be balanced over here, so it's not going to rotate any longer. So what we have to do in order for us to continue to rotate, we are going to introduce a north and a south. Therefore, we can continue the rotation. Now, we come across another big problem, right? Copy, paste. So we come to another problem, and that problem is that now it rotated, let me see here, it rotated counterclockwise. So it rotated counterclockwise, right? Wait, let me just double check. Sorry guys, it rotated counterclockwise. So let me erase this here, erase that there. It rotated counterclockwise, right? So what's going to happen is, because the current is flowing in the same direction, is going to be clockwise. Do you see a problem here? So what we have to do is introduce a commutator. So let me just copy this here, copy, paste. So therefore we are going to introduce a commutator over here, guys. We're going to introduce a commutator. So now we have fixed all the problems, and now it will be rotating very, very smoothly. Okay, so step 1, you need to increase magnetic field strength. Second, number of copper winding, yeah. So those are these wire. This is a singular wire I showed for illustration, but if you open up the electric motor, there are a lot of copper wires, and the reason why it's wires and not a solid piece of copper is something called eddy currents, which is quite difficult to explain. But basically, eddy currents is currents that create a resistance. It's not the correct definitions, but that is how I remember eddy currents. It is the a resistance created. That therefore, it is better to use copper wires instead of a solid copper inside an electric motor. And 3 is to increase current, and 4 is to increase the force. So these are the ways you can increase your power outputs or whatever such, depending on what you want. Okay, so let's move on. So the chapter we are busy with is AC circuits, right? So we have a question number 1. We have 3 coils, right? And we have 75 windings or turns. We have a speed of 1500 RPM. We have a magnetic field of 0,13 Tesla. We have a length of 0,3 meters, and we have a diameter of 0,125 meters. Okay, so number of turns would be small n, and number of windings 3, which will be okay. So now let's copy this diagram. Copy this diagram. Let's erase a few of the stuff. Okay. So we have our copper winding. You can also draw this diagram if you like, better understanding. Over here is our length, and over here is our diameter, right? So the first question is calculate the period, right? And to calculate the period, we know that the period is equal to 2 pi angular, right? So we're going to have 2 pi angular, which is angular velocity is equal to 2 pi n over 60, right? So then 2 pi over 2 pi 60 n, which is 1500, multiplied by the number of coils. So remember that you should multiply this by the coils. So to multiply by 3, and our period here would be 13,33 meters per second. Okay, sorry, not meters per second, period is in seconds. Now moving on to B, maximum value of induced EMF. So they want the maximum value of induced EMF. So we know that the EMF is equal to 2 pi BLBND. BNN. Okay, so we have 2 pi. B is for Tesla, which is 0,13. B, the L is for the length, 0,3. B is the width, which is multiplied by 0,125, and then N is RPM, and N is the number of turns. So we have 75 turns and 1500 RPMs, and our answer here is V is equal to 57,43 volts. Moving on to the next question, C. So they want the velocity, they want the voltage at 45 degrees. So the voltage at 45 is equal to the V max multiplied by sine 45, and our V max is 57,43 multiplied by sine 45, and we have an answer of 40,06 volts. And remember when I was explaining this concept here, right? So if you do sine 0 and you do sine 90, you will see that for sine 0 you will get an answer of 0. So this will be your minimum, right? And this will be 1, which is your maximum. That is where you get this from. So continuing with our next answer, D, what is the current? So we know that our current is voltage is equal to current is equal to voltage over the resistance, right? And then our voltage is going to be 40,61 over the resistance. So the resistance given is 25 ohms, right? And then we're going to put 25 ohms over here, and we have a current of 1,6 amps. So now A, B, C, D, E is the average EMF, which is the V max. So V average is equal to 0,637. This is just something you need to memorize, multiplied by V max, and your answer there is 36,59 volts. Moving on to question number F. So F says that they want the RMS, root mean square voltage. And to get the root mean square voltage, we're going to take the V max over root square, and we have an answer of 40,61 volts. And that would be it for today's lesson. If there are any questions, don't be afraid to ask, and I'll see you in the next video. Thank you and goodbye.